see today. We'll start on page 167. We'll begin exponential functions. So we're going to start off with an example we already know, which happens to not be an exponential function. Okay. You'll recall x squared. All right. We're going to compare it to 2 to the x. This is an exponential function. X squared is not, but we'll compare them, right? So here in this chart are just the coordinates for the graph of x squared here. All right. In an exponential function, the x is in the exponent. Your variable's in the exponent. They use b for the base, all right? B to the x. You can use whatever letter you want. They use b because that's the first letter of the word base, all right? It only works if b is not 1, right? Because 1 to the x is just 1, right? That wouldn't be an exponential function. So if we look at our chart here, all right, for 2 to the x, 2 to the negative 2, right? That's 1 over 2 squared, if you recall. Should be 1/4. All right. So if we go back 2, we'd go up to 1/4. All right. 2 to the negative 1 would be 1 over 2. So when we go back 1, we're back 1/2. Notice the further we go back, 2 to the negative 5 will be 1 over 2 to the 5th, right? Which would be 1 over, see, 2, 4, 8, 16, 32. So when you make it back to 5, you're all the way down at 1 over 32. So that's why when you go to the left, exponential functions do what we call decay. They drop off rapidly. They get closer and closer to 0 really rapidly. But when we go to the right, all right, you got 2 to the first is 2. 2 squared is 4. 8, 16, 32, 64. So when you're over here just at 6, you're all the way up here at 64. So when you go to the right, this thing does what we call exponentially grow. So we talk about exponential growth. So as compared to x squared here, right? When we're at 6, right? 6 squared would just be 36, right? Whereas down here, when you're at 6, you're all the way at 64, you know? When you make it to 7, you're at 128. Whereas the x squared, when you make it to 7, you're only at 49. Okay, so exponential functions grow very quickly. Let's see. We'll look at x squared. Put it in blue. And let's compare it to 2 to the x, which we'll put in light blue. It's kind of hard to see. Gray will work. So let's zoom out. So you see this gray line goes up faster than the blue line, right? So if you recall the compound interest formula, all right, the amount here is a function of time, all right? And you can see t is in the exponent. So compound interest is an exponential function, okay? Now our favorite exponential function is e to the x, all right? Just like pi is a mathematical constant that y'all know about, that appears all throughout mathematics and physics, all right? The number e, known as the natural base or Euler's number, all right, shows up all throughout math and physics. It occurs in nature pretty much everywhere. And it is 2.71828, and it goes on forever. That's just a rounded approximation, all right? It is a transcendental number. It's what we call the natural base for our exponential functions. So again, e is 2.71, etc. So it's really close to 2 to the x, right? Because it's 2.71 to the x. You know, it's almost 3, you know, closer to 3 than 2, but it looks a whole lot like 2 to the x. All the basic exponential functions look a lot alike, but this is our most important one, okay? They give us the chart over here. And there is a button on your calculator that has the e on it for doing e to the x, or e to any power you want. So when we look at our compound interest formula, all right, this part right here, right, if you let n go to infinity, okay, this 1 plus r over n to the n, as n goes to infinity, meaning the number of times you're compounding every year, you know, instead of monthly it'd be 12, weekly it'd be 52, daily it'd be 356. You know, as you go to compounding every second, or going past that and just compounding continuously, this thing here, this value approaches e to the r. Okay, so that's why this formula, as n approaches infinity, it approaches pe to the rt. All right, so this is our continuously compounding interest formula. You'd think that the more you compound the interest, the more interest you make, because you're collecting interest on interest, right? You'd think that if you did it infinitely, then you're collecting interest on interest on interest on interest an infinite number of times. You'd end up with an infinite amount of money. But that is not the case. It does plateau out. And this formula gives you the most amount of interest you can collect by compounding an infinite number of times in a year. So we will look at examples of that here shortly. All right. So let's look closely at some of these functions here. F of x equals 2 to the x, the domain. All right. Well, let's look at the y-intercept first. F of 0, 2 to the 0. Anything to the 0 power is always 1. So right here at 0, we go up 1. So there's our y-intercept. 0, 1. All right. As we go to the right, we have 2 to the first is 2. 2 squared is 4. We have 8, 16, 32. I go over 1. 2 to the first is 2. We go to the right 2. 2 squared is 4. I go to 3. 2 cubed is 8. At 4, all the way up at 16. So again, this thing has exponential growth. And when we go to the left, 2 to the negative 1 is a 1/2. 2 to the negative 2 is a 1/4, 1/8, 1/16, etc. So as I go to the left, this thing exponentially decays. It approaches 0. We have what we call a horizontal asymptote at 0. So our domain, this guy, it goes infinitely far to the right and to the left. So the domain is all real numbers. The range, however, notice it's up here. There's nothing down here. So it never becomes 0. All right. There's no number you can plug in for x where 2 to the x is going to give you 0. It's always more than 0. So you got 1 over 16, 1 over a billion. All right. 1 over 100 trillion. It just gets closer and closer to 0. So you want to have a round parenthesis here. It would be 0 to infinity because it does go infinitely far up. All right, now let's look at 5 to the x. All right, our y-intercept, f of 0, 5 to the 0. Again, anything to the 0 power is 1, so our y-intercept is 0, 1 again. Let's see. 5 to the first is 5. 5 squared is 25. 5 cubed is 125. So over here at 1, we got 5. At 2, we're at 25. We're already off of the paper. So this one grows just like the last one did, except it does it much more quickly. Okay, when we go to the left, we have 1/5, 1/25, 1 over 125. So when we go to the left, it exponentially decays just like the last function, but it does it even more quickly. So they look a lot alike. The only difference is this one is more intense than this one. I don't know if this will show it very well. If we grab a 5 to the x compared to 2 to the x. All right. You can see the blue one grows much more quickly than the gray one, right? It goes up faster, right? And it decays much more quickly as well. Let's see if I can take a snapshot of this guy. So in the blue here, 5 to the x grows faster than 2 to the x. All right. And decays faster down over here than 2 to the x, right? So you can see it's blowing up much more quickly than in the gray one. Otherwise, they look exactly the same, all right? They do share their y-intercept. All right, now let's look and see what happens when you make the x negative. All right, if you recall, making your x negative in a function flips the function over the y-axis. Because, I mean, 3 to the x is going to look like that. Well, it's going to go through here, and it's going to blow up, right? When you make the x negative, well, when we plugged in positive numbers, we went up, right? Now, if we plug in positive numbers, the 3 to the is going to get negative numbers. So when those positive numbers are plugged in, all right, you're going to have to plug in negative numbers. When you plug negative numbers in, the negative in front of the negative turns them positive. So this thing is going to look just like that. All right, it's going to be flipped. We can look at it point by point, though. Let's look at our y-intercept. F of 0 is 3 to the negative 0. 3 to the 0, which is 1. So same thing. Remember that negative exponent means put it on the bottom of the fraction. All right. So let's look at some points here. If we look at 1, that's 1 over 3 to the first, or 1/3. So if we go over 1, we have to go down to 1/3. If 2 would be 1 over 3 squared, which would be 1/9. If we keep going, we'd have 1 over 27. All right. So as we go to the right, this thing decays rapidly. But when we go to the left, all right, we have 3 to the negative -1, 3 to the first. So when we go back 1, we have to go up 3. -2, we'd have 3 to the -2, or 3 squared, or 9. We go back 2, we have to go up 9. When we go back 3, we'd have to go up 27. Okay. So when you make the x negative, again, it just flips your graph over the y-axis. We compare them here. Let's do a 3 to the x and 3 to the negative x. All right. All right, so in the blue is 3 to the negative x. So what is the domain? Well, this guy goes infinitely to the right, and it goes infinitely to the left, so all real numbers. The range, everything is up here, so from 0 to infinity, not including 0, round bracket there. All right, our simple interest formula, I par t, principal times your interest times your interest rate times your time. So your amount is your principal plus your interest, right? And the interest here is PRT. So we could factor a P out and we get a 1 plus RT, P times 1 plus RT. That's for simple interest. So like simple interest, if you say, here's your interest rate, and you're going to have a loan for, or collect interest for 15 years. Well, simple interest is you don't collect any interest until the end of the 15 years, and then you get that percent. All right, but typically things aren't done that way. Typically things are compounded at least annually. All right, you pay interest at the end of every year, or collect interest at the end of every year. Or even better, they compound it monthly. Like if you have a credit card, they charge you, if it says compounded monthly, then at the end of every month, whatever you owe, they take 1/12 of your interest rate, and they charge you that much interest each month. So for compound interest, if you recall, it's 1 plus r over n to the nt. All right, you can kind of see the relationship. We got the p out front, and then this guy turns into this. You know, got to get that n involved. Okay, where A is the amount after t years, right? A here is a function of time. P is the principal amount you start with, right? R is the interest rate. Usually means annually. Okay. So T is the time in years. All right. These two are related. All right. Because again, time is in years because the interest rate is annual. Okay. N is the number of times interest is taken in a year. Okay. Okay. See, annually, years, everything is based on a year. And now we have I'll just play. And then we have continuous interest. Continuous compounding of interest. Compounding of interest. The amount is PE to the RT, where E is 2.71. Euler's number. All right. It's our natural base. So if we're compounding annually, n is 1, semi-annually 2, quarterly 4, monthly 12, weekly 52 weeks in a year, right? Daily, and it would be 365. All right. Continuously, n is infinity. So again, n is infinity. So as n goes to infinity, this thing goes to PE to the RT. Hold on a second. Oh, that sucks. Sorry, your laptop died. That happens. Okay, let's see. All right. All right, we've invested $100. That's our principal at 2% interest. That's our interest rate. How much will it be worth in 15 years? All right, that's our time. If the interest is simple, okay, well, our interest, I par T, right? We have $100 times 0.02, our interest rate, times 15 years. So let's plug this into our calculator. So we have 100 times 0.02 times 15. So our interest is $30. So the amount we have is our principal plus our interest, which is 100 plus our 30, which is 130. So simple interest. At the end of 15 years, they collect interest, 2% of it, all right? 15 times basically. All right, now if we compound it annually, at the end of every year, we collect interest. That means at the end of the second year, we not only have our money and the interest from the first month, the first year, we also have the interest on the interest from the first year. So we're going to get a little bit more money out of this. So our amount, P times 1 plus R over N to the NT. All right. Our interest is 2%. In here is 1. So let's see. Inside here we got 1.02, 1.02 to the 15th power times 100. Gives us $134.59. So look, we got an extra $4, and that's from collecting interest on interest. All right, what if we compound it monthly? We got $100, 1 plus 0.02. Monthly, N is 12. So we got 12 times 15. So let's see. 0.02. Let's see, what is 12 times 15? This is 180. So 0.02 divided by 12 plus 1 to the power of 180. All right, times 100. This is $134.95. So we got an extra, 40 cents by compounding monthly instead of annually. If we go to weekly, 1 plus 0.02. Let's see, there's 52 weeks in a year. So we got 52 times 15. Let's see, what is this number? 52 times 15. That's 780. All right, if I figure that out first, I can more easily calculate this. 0.02 divided by 52 plus 1 to the power of 780 times $100. This gives us $134.98. So 3 more cents going from monthly to weekly. That's the extra interest on top of interest on top of interest. If we collect as much interest as we possibly can by compounding continuously, PE to the RT, we have $100 E to the 0.02 times 15. 0.02 times 15. That's 0.3. And now we do e to the, and now multiply by 100. We get $134.99. One whole extra cent by compounding an infinite number of times in a year. And that's the most you're going to get. All right, $800 is a principal. Time T is 5 years. 2.5 is our interest rate, right? It's 2.5% or 0.025. All right, simple interest, right? The amount we have, principal plus interest, principal plus simple interest, or principal times 1 plus RT, right? Principal is $800. Interest rate is 0.025, and for 5 years. So, let's see, 0.025 times 5, 0.025 times 5 plus 1 is 1.125 times 800 is $900. So we made $100 of interest. It's okay. It's fussy. All right, if we compound annually, we have our principal, 1 plus our interest rate over 1 times 5. All right, our compound interest we're in is 1. So we have 0.025 plus 1 now to the power of 5 now times 800, which is $905.13. So we gained an extra $5 by compounding annually instead of waiting till the end of the 5 years. All right. So monthly, 801 plus 0.025 over 12 now, the 12 times 5. So, I'm just entering this stuff into my iPhone calculator. I have to kind of start from the middle here. 0.025 divided by 12. And now I add 1 to that. And now I raise that to the 60th power. 12 times 5 is 60. So to the 60th power. Oh, I did something wrong here. 0.025 divided by 12 plus 1. All right. To the 60th power times 800. This is $906.40. So we made an extra dollar, 30. We compound weekly. Weekly, our N is 52. So 52 times 5. Let's see, 52 times 5. That's 260. All right. So I got a 0.025 divided by 52. Add 1. And now we raise that to the 260th power and then multiply by 800. Just $906.49. We got an extra 9 cents. Hourly. Well, how many hours are there in a year? 1 year. Let's see. I know there's 365 days in a year, right? And I know there are 24 hours in a day. So I got 365 times 24. 8,760. That's what our N is. The amount is 800. 1 plus 0.025 divided by 8,760 to the 8,760 times 5. All right. That number is 43,800, by the way. So I take 0.025 and divide it by 8760. Now add 1. And now I'll raise that to the power of 43,800. And now multiply by 800 bucks. I got $906.52, rounding up. It's really 0.518601. So the 8 rounds the 51 cents up to 2. I'm pretty sure banks would round down though. All right. And out of all the calculations they do, if they round down for every cent, that adds up to billions of dollars every year just from rounding to the nearest cent that they're collecting off of us. All right, now continuous. Oh yeah, let's compare. We got an extra 3 cents by going from weekly to hourly. Now F, continuous, the amount, again principal, e to the RT, 800 bucks, 2.5% interest, 5 years. All right, we have 0.025 times 5. I start up here, and I do e to the, and now I multiply that by 800. I get $906.52. This is really 0.51876. So you can see the difference here. It increased, but it's way down in the decimals. So, and the end result, you can't compare. You don't notice any difference between compounding hourly and continuously. All right, because the difference is too far down in the decimals. All right, the growth of bacteria colony. All right, it can be modeled by the function below, where n is the number of bacteria in thousands, and t is the time in minutes. All right, what is the initial population of the bacterium? All right, that's when t is 0. 25e. They have a k here. You can call it k, you can call it r. K is a constant. It has to do with the growth rate. All right, so whatever you want to call it, all right, K or R, doesn't matter here. We're plugging 0 in for T. So e to the 0, anything to the 0 power is just 1. So, and this is in thousands, so 25,000 bacteria. You can just look at it until at 0, this goes away, right? This becomes 1. You're just left with 25. So 25,000. The growth rate is 1% per minute. That means K or R, whatever you want to call it, is 0.01. How many bacteria would you have after 2 hours? All right. T is the time in minutes. So at 2 hours, that would be 120. All right. So N at 120 is 25 E to the 0.01. That's our rate times 120. All right. N is actually a function of K or R, whatever you want to call it, and T. It's a function of two variables, right? So we'll start with the exponent. 0.01 times 120, which would be a 1.2. So e to the 1.2 is 3.32. I multiply that by 25, and I get 83. So that means 83,000 bacteria in thousands. 83,000 bacteria. So only after 2 hours, the bacteria has gone from 25,000 to 83,000 in just 2 hours. All right, page 173. $7,000 is invested at 5% compounded daily. Find the total amount after 12 years. No withdrawals are made. All right, the amount, $7,000. 1 plus our interest rate is 5%, compounding daily, and for 12 years. All right, let's see. 365 times 12. All right. Is 4,380. All right. Once I know that number, I can do the rest of this in one step. So I start off with the 0.05. 0.05. Divide it by 365. 0.05 divided by 365. Now I add 1 to that. All right. And now I raise that to the power of 4,380. And then multiply by 7,000. And we get $12,754.30. All right. So that's not bad. Only 5% interest. 12 years, we've gone from 7,000 to 12,700. We got what, 5,700 bucks by doing nothing, just by investing. That's why it's important to have a savings account, you know, even if you don't have a lot of money, just putting aside a little bit you know, every month, whatever you can. You know, over time it adds up. You know, if you smoke cigarettes, you know, if you smoke a pack a day, if you put $5 a day into a bank uh, and collected 5% interest on that, and hell, in 20 years you'd have like, I don't know, about $115,000. All right, suppose that $10,000 is invested at 4.25. All right, that'd be 0.0425, compounded continuously and infinity. Find the total amount after 35 years. All right, our amount 10,000 e to the interest rate times the time. All right, I'll start with the exponent here. 0.0425 times 35. And now I'll do e to the, and now multiply that by 10,000. And we get 44,260 bucks and 17 cents. Well, that's not bad. $35,000 you're making in 35 years off of 10,000 bucks. All right. So more than tripled the money, and that's only at a 4.25% interest rate. All right. So again, save what you can. All right. This is how you retire. You know, even if you live paycheck to paycheck, you know, if you just could put aside just $1 a day, it'll add up to quite a bit. All right, here's our principal, 375,000. It decreased in value. So it decreased. So our rate here is a negative 0.035. Negative, because it's decreasing. What will it be worth in 2030? Well, time here is 14 years. Okay. So compounded annually, and is 12. So the amount, 375,000. 1 plus a negative 0.035 over 12 to the negative 0.035 times 14. All right, so sorry, that's not the interest rate. 12. All right, in the number of times we're compounding. The interest rate only shows up inside here. So let's see, 12 times 14. What is that? 12 times 14. That is 168. So knowing that, I can now tackle this thing with my simple iPhone calculator. I have negative 0.035 divided by 12. All right, so that's a negative number. So if I add 1 to that, all right, this number inside of here is less than 1. Okay, so now when I raise it to the 168th power, it's going to be even smaller. All right, so that ends up being like 0.6. Now I multiply that by 375,000. and I get $229,570.47. So in 14 years, decreasing at only a 3.5% rate, we've lost about $150,000 in value. All right, page 174. Now, you know what? Today's class is really long, so let's take a 10-minute break. We'll come back at 10:05. Okay, okie dokie, folks. Grab you a breakfast taco or something. All right, page 174. Tim, he wants to know which loan is better, Bank A or Bank B. Bank A is a 15-year loan. Bank B is a 10-year loan. Bank A offers 4.5% compounded weekly. Bank B is 10-year loan. Fewer years, but a higher interest rate. And they compound it continuously. And so he's borrowing $4,800. Which loan should he take? Let's look at Bank A. His amount is going to be $4,800. See, his rate is 4.5%, so 0.045. They're compounding weekly, so N is 52. And Bank A is a 15-year loan. So I find it easier just to find that exponent first. This 52 times 15, that's 780. Now I can enter in the rest of this in my calculator. I start with the interest rate, 0.045, divide that by 52. Now I'm going to add 1. I'm going to raise that to the power of 780 and multiply by 4,800. So he's going to end up paying a total of $9,424.60 for Bank A. Bank B, 4,800, an interest rate of 5.75, so 0.0575. Oh, it's compounded continuously. If it's continuously, I'll have to do this one. E to the R T, and the time is the 10-year loan. So that exponent 0.0575 times 10, right, is of course 0.575. So I do E to the, and now multiply by 4,800. So $8,530.22. So Bank B is the better choice here. You know, he'll save like $900 by going with Bank B. And he'll be done with his, he'll have to pay it off sooner, you know, but he'll save $900. All right, the amount of plutonium remaining from 1 kilogram after X years is given by the function W of X equals 2 to the negative X over 24,360. How much will be left after 1,000 years? We got 2 to the negative 1,000 over 24,360. So let's see if I take -1000 divided by 24360. This is 2 to the negative 0.04105009. Things like this, you always want to keep as many decimals as you can. So now I take 2 to the, let's see if I can get this in. Let's see. Actually, I'm going to use a different program. I can't get this into my calculator. I don't know how to do a negative exponent, because when I do the 2 to the, and then I hit the negative, it changes my to the to a negative. So I'm going to bust out Wolfram Alpha, and I'm just going to type it in 2 to the negative 1000 divided by 24360. All right. So this thing is telling me this is 0.9719. Again, this is kilograms. So we started at 1 kilogram, and according to the formula, it's decayed, right? This is exponential decay. It's decayed to 0.97 kilograms, so it decayed just a little bit. Let's look at 10,000 years. This is 2 to the negative 10,000 to 24,360. All right. So if I change my 1,000 to a 10,000, I get 0.7523 kilograms. So even though 10 times, it's been 10 times as long, 10,000 years instead of 1,000 years, we've only dropped a little bit, you know, like a little over 1/10 of a kilogram. So the longer it goes, all right, you'll lose more, but not at the same rate. The rate at which you lose, or the rate at which it decays, drops off quickly, you know. If we looked at 100,000 years, 2 to the negative, let's look at 100,000 years. All right, 0.0581. So that's, you know, at 100,000 years, we still have a little bit left. All right, it'll never go completely away, right? This it would take an infinite number of years for this to go to zero. So the plutonium will never completely go away. All right, this one tells us about the amount of milligrams of morphine in the bloodstream. All right, the initial dosage is at hour 0. All right, so M of 0 is 10 e to the negative 0.173 times 0. I didn't mean to make e as an exponent. 10 e to the 0 power, e to the 0, anything to the 0 power is 1, so it's just 10 milligrams. We can just look at it and go, okay, plug a 0 in here, we're just left with the 10. So we start off with 10 milligrams. All right, after 1 hour and after 4 hours. 1 hour, that's 10e to the negative 0.173 times 1. So, let's see, negative 0.173 e to the, now times 10, equals 8.41 milligrams. So we started off with 10. An hour later, we're down to 8.41. 4 hours later, so let's see, if I take negative 0.173, multiply it by 4, and now do e to the, now multiply it by 10. We got 5.0 milligrams. So it takes 4 hours to lose half of the initial dosage. So here's your homework for exponential functions. There we got 1, 2 pages of homework, not bad. All right, inverse functions. So we're going to look at an example here. We're going to look at 2 to the x and compare it to its inverse, x over 2. Okay. Why are these inverses? Well, they undo one another. The opposite of multiplying by 2 is dividing by 2. Consider if you plugged in g of x into f of x. All right, f says take your input and multiply it by 2. So up here our input is g of x. G of x says divide by 2, so we get 2, replacing g of x with what it says. 2 times x over 2 is just x. All right, if you do one and then the other, they undo one another and you're left with just x. Or if you did it in the opposite order, if you plugged f into g, well, g says divide by 2, so we have f of x over 2. But f of x says multiply by 2, so we have a 2x over 2, which is just x. All right, they are inverses of one another. All right, there is a notation. G of x is f inverse of x. When you put a negative 1 to a function like that, they do not mean 1 over. All right, it means the inverse. All right, g is f inverse, and vice versa. So let's look at our charts here. So if I plug a 2 in over here, 2 times negative 2 is a negative 4. 2 times negative 1 is a negative 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Now over here, for g of x, if we plug a negative 4 in, negative 4 over 2 is 2. Negative 2 over 2 is a negative 1. 0 over 2 is 0. 2 over 2 is 1. 4 over 2 is 2. 6 over 2 is 3. So compare these. Negative 2, negative 4. Negative, I forgot my negative there. Negative 4, negative 2. Negative 1, negative 2. Negative 2, negative 1. 0, 0, 0, 0. 1, 2, 2, 1. 2, 4, 4, 2. So notice x and y's have switched places. Okay, the input for one is the output for the other. So if we graph these, all right, let's look at 2, so what was this, 2x? 2x compared to x, x divided by 2. Make this pink. All right, so this is the blue is 2x and the pink is x over 2. Notice 2x has a slope of 2, whereas x over 2 has a slope of 1/2. Now look at this function. F of x equals x. That's just the diagonal. All right, so the inverse, if you have a function, the inverse of that function, its graph is just going to be a reflection over the diagonal. Okay, let's take a snapshot of that. All right, again, 2x, if I go, I'll go through the origin, right? 2x, if I go over 2, if I go over 1, I got to go up 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 4 is 8. Okay, but the x over 2, all right, 2 over 2 is just 1. 4 over 2 is 2. 6 over 2 is 3. 8 over 2 is 4. All right. These values are just being reflected over this diagonal, right? The 45-degree line, f of x equals x. But again, it's the same. The input is the other one's output. That's what it means for them to be inverses of one another. All right, if you do one and then do the other, you end up with what you had, right? If you double it and then half it, you have what you started with. And the reason why this is important is we have to figure out how to undo the exponential function. So let's look at these. These are two examples. All right. If you add 5 and subtract 5, you just get your x back. If you multiply by 6 and then divide by 6, you have your x back. If you multiply by 3, divide by 3, you have x. If you subtract 2, then add 2, you're left with x. If you take 4 and square it, then square root it, you get your 4 back. If you take your 6, square it, and then square root it, you just get your 6 back. All right, so this is an example of squaring and square rooting. All right, so what we're looking at here is g of f of x. All right, g says take your input and square root it. So square root of f of x. And f of x says take your input and square it. All right, on each of these, you're just getting your number back. Remember the square root means to the 1/2 power. And when you raise an exponent to an exponent, you multiply. Okay. They like to throw these in here. I'm not really sure why this is thrown in here, but I guess it's just reminders of how to do this because it's important. 45%, 45 out of 100, which is 0.45. 18.25%, 18.25%, 0.1825. 0.15%. That's 0.15% or 0.0001. Hold on. All right, yeah, 0.0015. 12 9/10%. That's 12.9% or 12.9 over 100 or 0.129. 0.005%, that's 0.005 over 100 or 0.00005. Negative 2 1/5, that would be a negative 2.2% or negative 2.2 over 100. Hold on. Sorry, my cat jumped my baby's phone. So we got negative 0.022. Yeah, move the decimal to the left twice. And one more. So this is a negative 0.269 over 100 or negative 0.00269. All right, moving the decimal to the left twice. So let's look at this problem here. 7,000 is invested. Our interest rate is 8.5%. How long will it take the investment to grow to $10,000 if it is compounded continuously? All right, well, how much money is being invested? 7,000. Interest rate is a percent, 0.085. All right, or 8.5%. The final amount of money, the amount is 10,000. What is the unknown? They're asking for the time. So we know amount equals PE to the RT. We need to rearrange this equation to get T by itself. How do we do that? Well, let's see, we can divide both sides by P, right? So I'll end up with the E to the RT is A over P. Now, how do I get the T out of the exponent? I need to undo this exponent. Well, there's the inverse of the exponential is called the logarithm, also called the log. All right. So if I have a b to the x, I take log base b, and that gives me my x back. Okay. And if I have b to the log base b of x, I get my x back. All right. So to undo the exponential, you take a log. All right. And to undo a log, you do the exponential. So b to the log base b gives you your x back. So what we need here is we need to take log base e of both sides. If I take a log base e of both sides of this thing, all right, the log base e and the e to the undo one another, and I'm left with RT. All right, so now I can just divide both sides by R. So that's how you find the time. We need to do the inverse of the log. Now, your calculator has two buttons. It has a log base 10 button, and it has this, ln. ln is the natural log, or log base e. Remember that E was called the natural base for exponentials? Well, the natural log is ln on your calculator. So if we want to figure this out, we have our formula for our time. So we need log base E, also known as ln. The amount that we want to end up with is 10,000. The amount we start off with is 7,000, our principal. And our interest rate was 8.5% or 0.085. So we got 10,000 divided by 7,000, which is 1.428. And so we take the natural log of that and now divide by 0.085. We get 4.196 years. All right. So, I mean, every function has an inverse, but for exponentials, we use logs. All right. There's an infinite number of them. You can do log base anything. All right, number 20 here. All right, $7,000 is invested at 8.5%. So far, it's the same as the last problem. How long will it take the investment to double if it's compounded continuously? So the last one, we wanted to know how long it got to 10,000. Now we're looking at, for it to double, that'd be 14,000. Okay, so that's how it differs. Instead of going to 10, we're going to twice our original, which would be 14,000. We're looking for the time. So we use our formula. So log base E is also known as natural log. The amount, all right, was twice our initial principal. So amount is twice P. All right, so it really doesn't matter what you start off with. All right, if you're doubling it, it doesn't matter how much you start off with, you're going to get the same answer. All right, because whatever the principal is, you take 2P over P, you just end up with a 2, no matter what the principal is, as long as you're doubling it. Oh, and our rate here is 0.085. So if I take 2 and then press natural log and then divide by 0.085, we get 8.15 years. So at this interest rate, it doesn't matter how much you've invested, it's going to take 8.15 years to double your money if it's compounded continuously. All right, let's call it a day, and we'll get back to this on Monday.
Yes, sir.
All right, thank you, folks.
Have a good day, sir.
Y'all
Thank you.
too.
Have a good one.